question 4. The collision of two bowling balls is modelled as a perfectly elastic collision. A light bowling ball, 5 kilograms, is travelling at 4.7 meters per second and collides head-on with a stationary heavy bowling ball of 7 kilograms. Draw a diagram of the bowling ball before and after the collision, labelling the important values. So we're going to have our 5.0 kilogram ball travelling 4.7 meters per second, and we get our 7 kilogram ball, which is stationary. And then after, we've got two velocities that we don't know. So this one still is 5.0 kilograms. This is still 7 kilograms. And I'm going to label them both as having a speed. I think there's various arguments here as to what to do. I tend to label them both going to the right. I think looking at this collision, I expect U to be negative when I eventually work it out, but as a standard convention, I normally label them to the right. That's just the way I like to do it. There's no reason we have to do it that way. Write an expression of the momentum before and after the collision. So we know the momentum before should be equal to the momentum after. So let's write it down in one line. So the momentum before is 5 times 4.7. That's 23.5. That should be equal to the momentum after, which is 5u plus 7v. So I've used u and v for the two speeds. They're the two speeds afterwards. So I know previously we've used u before and v for afterwards, but u and v tend to be the labels we use when there's two speeds as well. Kinetic energy before and after. So again, because we're, as it's set up here, modelling as a perfectly elastic collision, we can say that the kinetic energy before should equal the kinetic energy after. We know that kinetic energy is half mv squared. So half 5 times 4.7 is 55.225. We'll leave it as lots of significant figures because if it was an exam question, it would have to log that value. Because it's a choice time question, we're going to try and work out an exact value and then round it at the end. So that should be the momentum, so the kinetic energy before, half times 5 times 4.7 squared. Afterwards, we've got half times 5 times u squared, so that's 2.5 u squared plus half times 7 times v squared, so that's 3.5 v squared. So now we've got two equations in u and v, numbers next to each other, 1, 2. So in part C, we're going to combine the equations to find the speed of two balls. So we need to deal with these simultaneous equations. My preference at this point would be to use a bit of a trick to keep track of what I'm doing as I go along. When you do momentum questions, one possible solution for the momentum is conserved and the kinetic energy is conserved is that this ball never collides with the first ball. So I expect one of my results to be that ball, 5 kilogram ball, has a mass of 4.7 meters per second, and that the 7 kilogram ball has a mass of 0, a speed of 0. Now, knowing that this one's going to have a speed of 0 as one of our solutions means that it's sensible to try and find v first. That's because I expect when I try to find v, I'm going to produce a quadratic, but where 0 is one of the solutions. And so that's going to mean I have to do a lot less manipulation in the end. So this is a useful trick if you know it. If you don't know it, it's easy to go down the wrong path because it's tempting to think I should find u first because it's first. We're not going to do that. We're going to try and find the value of v first. So from equation number 1, I'm going to get an expression for u in terms of v. So I need to divide through by 5. So 23.5 over 5 takes us back to 4.7, wasn't it? Because 23.5 was just 5 times 4.7. And then plus 7 over 5. So that's, sorry, that's going to be minus, isn't it? Minus 1.4 v. So then I want to put that expression that I've just got in for this thing here. So rather than having to manipulate it all in here, let's work out what the value of 2.5 u squared is down here. So I have to remember that this is effectively in brackets. So, and then I'm going to multiply out my brackets as I square it, and then multiply by 2.5 as I go along. So here I need to do 4.7 squared times 2.5. That value is 55.225. We notice immediately that this is the same as this value up here. Well, this is exactly what I was just saying. One of our solutions is going to be 0. So we should expect those two numbers to be the same. Actually, it shouldn't really come as a surprise. So we've got this term, then let's do the v squared term next. So we're going to do 1.4 squared, but then also times the 2.5 that we've got over here. So 1.5, 4 squared times 2.5 is 4.9 v squared. And then we've got our two sort of cross multiplying terms. So 4.7 times minus 1.4 in the other bracket, and then the other pair as well, minus 1.4 times 4.7. So we're going to do 4.7 times 1.4 times 2 times the 2.5 that we have over here, which is 32.9 V. So now we've got the value of 2.5 u squared. We can put this in to equation number 2. So we're going to take this and feed it into equation number 2. When we do that, we get 55.225 is equal to 55.225 plus 4.9 v squared minus 32.9 v. And then an easy mistake to make at this point is to forget the last term here, so plus 3.5 v squared. Immediately, we can say that these two terms are equal to each other. Once we've done that, we can see that everything has got a v in, so we can divide by v. This side is now equal to 0, isn't it? So we can divide through by v. And so we've just got 4.9v plus 3.5v, so that's 8.4v, should be equal to 32.9. So v is equal to 32.9 over 8.4, which is 3.92 meters per second. We can now take that value for v and feed it back into this equation that we had to start off with to find a value for u. And our other value for u then is 4.7 minus 1.4 times this, which comes out as minus 0.78 meters per second. So as we expected, u was a negative number. The 5 kilogram ball does bounce backwards, but doing it this way means we get a negative sign at the end.